So why go and mess that up? So, but we will work under this assumption. Yes, Grace?
Why exactly is the static friction greater than the kinetic?
Since if I have two surfaces pressed against each other so that normal force is the same in these two situations, the idea is that it's harder to get it moving, but once you get it moving, it doesn't require as much force.
Okay.
And so that's why the breaking point is greater than the effort that will be spent after that.
Okay.
Now, if I look at student results of labs, well, sometimes I get negative, I've gotten negative coefficients of friction. I've had UK bigger than US way too many times. So just recognize when you do a lab with friction, just try to be very, very particular about it. So let's actually do a run through here and let's calculate some values. Similar setup to what we did yesterday. Oh, oops. I actually don't want it sliding. So I want to put, sorry, I don't want it to be rolling, I want it sliding. Ooh. How about one of these? Nah, I'm gonna grab a box. I'll be right back. I'm just gonna let that run. All right, so we need sliding going on, so this. Can't break it. Oh, no, I can just disconnect it. Let's get a loop in it. Downside of nearly invisible thread. All right, it is sliding. We've overcome static friction, sort of. This would, and to make it more interesting, let's put it on that. All right, so I need to see how much force is required or how much mass is required in order to get that to start sliding. So I've got 70 grams on the end there. Let's add a 200, see if that is enough. $200 is definitely enough. Let's take one of these off. All right, so well, that's 100. I had 150 on there, so let's try 170. Now, I am limited here because I don't have a slew of masses. And what's going to add? I gotta be approaching 200 here. See if I can get it. So it doesn't need much to get going, so it's really close. Ooh. Okay, now it's too much. In my mind's eye, I always picture this part taking a whole lot faster, or being a lot faster than this. All right, that seems, it's gonna be somewhere around there. Now, it would have been helpful if I had cleaned off the track, just to make sure that the surface was as close to the same throughout. But let's just pretend that that is that point where it's barely moving. If I just touch it lightly, it seems to move more than I'm just touching it, so I'm really near that edge there. If I trust the manufacturer, which I will for the sake of this, it's 170 grams hanging off the end. So I got my cable, got my track, got the pulley, I have my sliding box, and this is about 170 grams. I have 500 grams there, and the box, I'm gonna say is about 60 grams. So I have 560 grams right there. It's the box plus what I put into it. Now, in an official lab, you would find the mass of them, and we have a balance and we could do it, but just for the sake of time, you found mass before. You would know how to do it. You would know how to do it. All right, so this is the situation here. Now, the force that's driving all of it, that without which it would not move at all, is the weight here. It is this weight that is causing it to move. Okay? F equals ma. I know my acceleration is going to be 0 because I don't want it, I'm looking for that breaking point, that the little bit of mass it takes to get it to move is so close to the little bit of mass, to the most mass that it won't move. We're treating them as the same. And so the weight is the driving force. The total mass that is moving, and then opposing it, too much in yesterday's mode. So I have weight driving it, and I have the friction up here that's opposing it. And that's equal to 0. We're dealing with static friction. I know weight is mg. I'm going to add that to the other side. That's equal to my static friction, max. And this mass, this is the hanging mass, so mh. My static friction is my static coefficient times the normal force. And my normal force, that's the normal force here. The normal force between the track and this car, and the block here, in the wood. So if I treat this 560 gram object here, it has a weight acting down, friction's acting back, there's a tension acting that way, and a normal force acting up. That's the normal force I need to identify, which should just be equal to this weight. That's hanging weight. This is my think in the lab I call it T for track weight. So my normal force is just gonna be that, because it's not accelerating up or down. So that's mus times the track mass, g. What I'm heading towards, I mean, if you want to plug in numbers earlier, that's fine. What I'm heading towards is a simplified version of this. Showing, and the main reason I'm going through all these steps is just to show you it comes from somewhere, which is where most of my derivations, or why I do my derivations, is just to show you it's not, hey, here's an equation, plug in. So I have the hanging mass times acceleration due to gravity is equal to my static friction, which is u sub s times the track mass times the acceleration due to gravity. I'm trying to solve for mu sub s. I need to get this all by itself, and I got multiplication, so I undo multiplication by dividing. I'm going to divide both sides by mt and g. MT's cancel out, the G's cancel out on the left hand, on right hand side. Bless you. Over here, the G's cancel out, and what I'm left with is my static coefficient is just equal to whatever my hanging mass is divided by the mass on the track. So it boils down to all this stuff using Newton's laws and the definition of weight and our formula for friction. It all boils down to, in this particular case, our static coefficient, 170 grams divided by 560 grams. Or if you prefer SI units, 0.170 kilograms divided by 0.560 kilograms. And someone will be kind enough to calculate that. And what will the units be?
Kilograms?
Why kilograms?
Because that's what it was before we divided. It would be grams.
If I did 4 divided by 4, is the answer 4? Because that's what it was beforehand. Over here, I have grams on top and bottom. They cancel. I have kilograms on top and bottom. They would cancel. There are no units. It's just a number. If I plotted, because again, everyone loves a graph. Ultimately, it's the hanging mass divided by, over the track mass. So if I plotted hanging mass versus the track mass, the coefficient of static friction is just the slope. Equals so that way if I'm a little bit off in one place but a little bit off in the other direction, another place, they should all balance out. And so that's the main reason why you would plot it to do the slope as opposed to doing each individual trial. Questions? All right. I know what you're thinking. Hey, that's great, static's fun. What about kinetic? What's the kinetic coefficient? Well, I'm glad you asked. Glad you were thinking that. All right, so we're gonna do something very similar to what we did Monday. I just need this thing to slide. So I'm gonna throw the 200 on there. Is that enough to get it to? That is not. So what I want to do is I want to make sure that this thing is going to slide. That seems to definitely be sliding. Let's put that there to keep it from sliding for right now. We just happen to have a LabQuest right here that hopefully is ready. A motion sensor. Should be bringing back some fond memories of the other day. Let's see, the motion sensor goes in here. It's not measuring. Now I want to get this lined up as nicely as possible. You know, if it's off at an angle, it's going to be thrown off a little bit. It should be registering the back of that, and it says it's 0.44 meters away. And that is 10, 20, 30, 40, and a little bit, so that's roughly right. Now the actual position doesn't matter, it's the change in position. The change in position, that really matters. So all we need to do is just record this thing sliding, just as you did before. Now again, in order to get more accurate results, right now it's doing 20 samples a second, so I'm just going to change that to 50. And just to give me a little extra time, I'm going to make it 20 seconds, although I don't need that much. And so right now, 20 samples a second for 20 seconds. If you ever do too much, so if you did 50 samples a second for 1,000 seconds, then it will tell you how many samples, it tells you how many samples it's going to take. If it's too many, it will be in yellow or red. I think yellow is a warning, red is, yeah, that's not going to happen. I would go higher than 50 samples a second, but that's all it can do. So I would start that, and then I'd let this go. Let's see, let's make sure that that string is as horizontal as possible. Is that horizontal? I got a nod.
From my angle, it looks like it is.
It did, okay. And I really don't want it crashing into the pulley. So what I'm going to do is, yeah, what could possibly go wrong? Actually, what will go wrong? Nope, that's going to smack into the pulley. Could I have a volunteer to come up here and keep it from smacking into the pulley? Someone to put their hand there. Thank you. So just, all right, hit the green triangle, get it started. All right, thank you very much. Let's see. Graph, share graph, graph one. All right, I'm hoping you can see that. I guess, Chikara, you're the farthest away. Can you see it?
I think it's one at this angle.
Yeah, it starts out sort of flatline and then it curves up and then it levels off. All of you face this on Monday. So, it's like that. I haven't let go. I suddenly let go. It zips up like that and then comes off. There's some jagged parts in it. the part here was when it hadn't moved yet. The part here is after it hit Emily's fingers. So I want to highlight a section in here which looks nice and do the curve fit. And analyze, curve fit, position. And so I've got the two black brackets which tell me which part is actually going to be mapped or modeled. Then I go to quadratic. And A is 0.57797. 57797. 57797. I think, is that what it said? All right. As before, that's half the acceleration. So my acceleration is 2 times that. Is that right? I'm not opposed to making Keller's error up here.
Yeah, that's right.
All right, okay, and units? Acceleration?
Meters per second squared.
Yeah. This also has units of meters per second squared, but it's not acceleration, it's half the acceleration. All right, so let's see what we got here. Looking at our diagram over here, again, the driving force behind all of it is the weight of what's hanging, which is, my mass is 300 grams. So I've got, I know it's weight minus the friction. So weight's driving the whole thing. The friction up here is what's holding it back. Is equal to mass times acceleration. Again, this is Newton's second law. My weight that's driving the whole thing, this is the hanging weight, and this is the friction on the track. This is total mass. Total.